Hi everyone, welcome to our last session in our BERD Academy course, Understanding Uncertainty in Data-Driven Research, or How Uncertainty Shapes Machine Learning, where in this session we will look at uncertainty in large language models. And today we start with first looking at how large language models work. Imagine we have I get my laser point again. Imagine we have a task like that. We want to predict the next word in a sequence. For example, the cat likes to sleep in the We can basically also use a neural network for that, where the next word is then predicted, for example, to be box with a probability of 8%. There are many other words that are also possible, but in the end we just want to predict the next word in a sequence. This looks basically like a very simple classification setting that we already talked about. Obviously, large language models don't only predict one word, but they predict basically multiple words then in a row. And also, if you remember that for all the models or all the machine learning models that we want to get, we need a lot of training data. I can show you how to get training data for language examples. Basically, if we already have a sentence like the cat likes to sleep in the we can basically take the very first word that we have as context and predict the next word. We can then take the first two words and predict the third word. Can take the cat likes to predict to, the cat likes to predict sleep, the cat likes to sleep, and then we want to predict in. And basically we can generate our training data like that by step, just taking existing sentences and acting like we don't know what comes next and wanting to predict that. To predict in the end the next word in any sequence. And the training data for large language models is really massive and can look like that, for example. This is an open source LLM data set. I just take it as an example because in reality we don't really know what neural networks are trained with, because the big companies usually keep this information hidden. But for example, what can be in there are research papers, for example, about like medical things. Archive is more for like computer science, math, and so on. We can have some informations about legal papers and so on. We also just have the internet, so websites like Wikipedia, Stack Exchange, and just many websites that exist out there. We also have books, basically. So imagine any book that you've read. Possibilities are if it was digitalized, that it was in open source data sets like that. But also companies nowadays literally just buy books, scan them, and use that for training data as well. Here on the right, I'll move a little so you can see it. We also have just computer code. So for example, GitHub was scraped as well and used as a training data. And the last category are just like some dialogues, like subtitles and movies and so on. And as you can see, the training data is very diverse. That's the reason why LLMs can then predict the next word in any sequence, and also it can be the next word in computer code, for example. And now if you not only predict one word at a time, but do that like a lot of times, like a lot of steps, you can basically get the whole outputs that you are used to when you are prompting your favorite LLM. So imagine basically a task like just summarize this whole paper for me is also just predicting the next words based on your prompt and the text that you want to have summarized. Okay. And LLMs have different phases of training. there is this so-called pre-training. So this is just this predicting the next word in a sequence, what we've looked at first. So this is only the very basic step of large language models. And there they learn like a general language structure, maybe facts and reasoning, because they just saw a lot of examples. Then there is instruction fine-tuning. So imagine the task of summarizing an article or a paper. This is something that needs to be taught to the LLMs. And this works by having this high quality curated prompt response pairs verified by humans. So you basically show them example what summarizing an article should look like, or answering a question should look like. And then because tasks like that usually don't exist in the training data so far, because at the beginning when LLMs were invented, there were no LLMs before where you could have had examples of how these instructions should, or how the instructions should lead to results. The last phase is reinforcement learning from human feedback. Reinforcement learning is a general technique that's also used a lot in robotics, where basically your robot or LLM learns to figure out what are good actions by either getting a reward or not getting a reward. And for LLMs it works like that humans can rate the outputs they get from the model. So the model just tries something, it gives you some kind of output, and you say this was a good output and the other one was a bad output. And it tries to improve, it wants to get better and better and better outputs. And in this way, by treating the user ratings as the reward model, the LLMs get better, more polite and more accurate. Okay, and since on the pictures you saw very, very small neural networks, I just want to raise awareness that those models are really, really huge. Nowadays, it started with like 100 million parameters back in 2018 with GPT-1, and the size increased. But the big problem is in this scale, you can see that all the blue dots are open weight models, so where the actual weights were published. However, if we look very closely, you see other GPT models, Claude model, Gemini, they are all missing because those companies decided to never release their parameters, but you can just access the models via their API or like the websites and so on. So we have no idea what's the parameter count of all those models. I just put them here so you can see the timeline with, for example, Claude Fable was published recently, or even more recently, ChatGPT 5.6 as of July 2026. I don't know when you will be watching this video again. It probably will have changed. But what I want to tell you with this slide is, first of all, the models are really huge. And second of all, many of them don't have the weights open. And for uncertainty quantification, some of the models rely on open weights because you really need to have like the probability of the tokens, for example, that are predicted. And so when we will look at the quantification methods, I always want you to think about, okay, what is your application case? Do you actually have access to some model weights, or do you not have access to your model weights because you're, for example, using Claude or OpenAI's ChatGPT or Gemini or whatever. And since it is like a very big discussion whether weights should be open or not, actually a lot of major US tech companies like Microsoft, OpenAI, Google, Meta, NVIDIA, basically all of the big tech companies, but Anthropic, they did not sign this letter. They wrote a letter to the US government, basically, where they specifically ask that policymakers should support open weight AI. So they should not prohibit that those companies are allowed to publish their weights in general. I mean, many of the companies don't do it either way, but it's different if they're basically forbidden to do so. And they argued that open weights models expand access, increase competition, and also strengthen AI safety through transparency. Because if we don't know what's happening in the weights or how the models work exactly, we can't really control what's happening there. And yeah, it's just important to say that even though LLMs are a quite technical topic, since it's more and more important in society, it also has political consequences. Thanks for listening to this session, and see you in the next one.